Hello everyone. Welcome back to the Yebo Twitter channel. And today we'll be looking at newtons again, but the second part of it of inclined plane. So on the previous video we looked at a flat surface, so we're going to be looking at incline. So without wasting any further time, let's get into it. Okay, so last time we talked about what happens when an object or a block is on a flat surface. But now I want us to talk about what happens when we mentioned it briefly in the last video, but today we're going to get into it. What happens when suddenly my surface is changed? So now I have an angle, and my block is now no longer on a flat surface, but it's now on an incline. And to better understand this is that let's refer back to our forces, like the one you mentioned first, the normal force. We said the normal force is perpendicular to the surface. So even when on an incline, we mentioned this briefly last time, that even on an incline, your normal force will still be perpendicular for 90 degrees with the surface, because your normal force has to be perpendicular to the surface. So it doesn't matter on how your surface, whether it's on an incline or a flat surface, your normal force always perpendicular. So remember that. And your gravity always going down. Now remember, your friction when on a flat surface, your friction is parallel to the surface. Even when on an incline, so depending on where the block is going, but your friction will also be force of friction will also be parallel to your surface, obviously depending on whether the block is going up or going down, because friction opposes the motion of an object, so it will go in the opposite direction to where the block is going. Now when we mention, so that's friction, then if there was a force applied, obviously friction will be going that way. Let's say force applied up, and we'll see, we'll do a scenario. I will get into an example where it has this, but it's even more complex because it has two blocks and it has one hanging and the other one on an incline. Okay, so that's friction. So now, if you still remember what we talked about last time on the other video, and if you have not, or if you're struggling to remember what happened, you can go back to it and rewatch it. I've explained most of the things there. So now, on your free body, when it comes to your free body diagram, because you'll be asked to either draw your free body diagram or your force diagram. And I said your force diagram, it's a block, your free body, it's a dot. But the marks indicate a number of forces you have. So in this case, if I was told that this block is stationary and the force is acting on it, and let's say I didn't have force applied, I didn't have anything applied, the block was stationary. If that was the case and I was doing a free body diagram, the force that's always there, that will be force of G, which is force of gravity. Then I will have, now my normal force, you see I'm not drawing my normal force straight, but instead I'm drawing my normal force at an angle. Why? Because this is the surface. If you think about it, this is the surface. This is the surface. So my normal force has to be perpendicular to the surface. If I draw it here, this is not perpendicular to the surface. So that is why I draw it at an angle. And then my force of friction will be also this way. Notice that my force of friction is also not in horizontal, but it's at an angle as well. Why? Because my surface is at an incline. So that will be the difference. So even my force diagram, that will be the same thing. My normal Fg, then my F of K. Simple as that. And now what you need to spend time on is the gravity. We mentioned it a bit on the last video, but we're going to dive into it a bit more now. So we talked about force of gravity, and we said force of gravity has components. This component, we have a component that is, because we said on an incline your normal force is not equal to your gravity. So because why? Because your normal force will be in this direction, perpendicular to the surface, and as you can see, your gravity is straight down. So instead you will have a component of gravity going this way. So this component of gravity will be equal to your normal force, and this will be Fg perpendicular. Fg perpendicular. Now, after that, you also have a force. You'll have a force, another component in this direction, and this one we call Fg parallel. So those are your components of gravity: Fg perpendicular, Fg parallel. And look at this: if my incline was in this direction, I would have my normal, then my Fg parallel will be, Fg perpendicular will be this way. Then you'll see, because my Fg parallel is this way, then that means my Fg parallel will be this way. Because my f of g, my gravity is downwards, my f of g parallel will go this way. Now if you notice something, I want you to notice something. You notice that regardless of the incline, whether it's in this direction or in this direction, notice that my Fg parallel is going down always. So that is what you should know about the direction of your Fg parallel. Fg parallel is always going down the incline. So if there ever comes a scenario where you are calculating a scenario and you notice that, no, my Fg parallel is going up the incline, then you should go back and check again, because Fg parallel always down the incline. Same as you see in this scenario, Fg parallel always down the incline. Notice that. So just make sure you notice that. Okay. So yes, and then others will better explain them when you go into questions. So let's look at the question. Now we have block M of 10 kg is connected to block M of 2 kg with a rope T of negligible mass over a frictionless pulley. Both blocks are at rest, so they're not moving. The slope makes an angle of 30 degrees with the horizontal. Friction on the scope cannot be ignored. So let's not ignore friction. Okay. 2.1, define term normal force. So these are the definitions you need to know: your normal force, your frictional force, Newton's first law, Newton's second law, Newton's third law. Those are the kind of laws you need to know, especially for Newton's. And sometimes they will ask that application question: how are seatbelt safe, or how do seat belts help? And you need to explain in terms of Newton's first law, moment that is called the law of inertia. So you must know that as well. So the second question says, draw a label free body diagram of all the forces acting on there. Let's take that down a bit. Acting on the 2 kg mass. Okay. So the 2 kg mass. So all the forces, so you see it's 2 max. So if it's 2 max, that means you know that we're going to have how many forces? We're going to have 2 forces because it's 2 max. So in that case, you're going to have, it's free body, you're going to have a dot. Then you're going to have what? We're going to have 2 forces, the other one going up and the other one going down. So this one will be force going down Fg, which is my gravity, and the one, this is not normal force, because remember, normal force is when on a surface, but this one is hanging in the air. So I have tension because it's hanged by a rope. A rope is hanging on to the 2 kg mass. So that is tension, because we're doing for the 2 kg. Now if we're doing for the, let's let's do another one for the other let's do another one for the 10 kg block. 10 kg block, standing still, so that will be normal force in this direction, gravity straight down, because they said friction cannot be ignored. So that means friction will be up the incline. And the reason I say friction up the incline, not down the incline, is if you notice the other one is 10 kg, the other one is 2 kg. So that means because of its mass, it will be trying to, the block will try to slide down the incline. It will be forced to slide down the incline because of it's pulling the other one. So it will try to pull the 2 kg mass down the incline. So that means the force of friction will be going up the incline, trying to prevent the block from moving. Okay, calculate the frictional force needed to keep the block at rest. Okay, so we need to calculate the frictional force needed to keep the block at rest. So already been told from the previous statement that already the block is at rest, so we know for a fact that the block is not moving. So because we need to calculate the frictional force needed to keep the block at rest, we can calculate the frictional force at this point where 10 kg block is, because already at this point the block is not moving. So then F net is equals to MA. And we know from that we have our forces of, so we have, because it's a block, we have FG parallel going down the incline, and we have tension. Oh, so this is what I forgot. On this block, the force that I forgot, force of tension. There will be 4 forces on that block because there's tension also. Because remember, there's tension on both blocks, because the other one is pulling tension up, but the other one is trying to pull the tension to the right up the slope. So F net is equals to MA. So then I have tension, I have friction. So as you can see, I have tension and friction go in the same direction. So I can say tension, because they're going in the same direction, it will be plus friction. So the block is standing, there will be force of static. Remember, we have 2 types of friction, static and kinetic. Kinetic when it's moving, static when it's standing still. Minus FG parallel. Why FG parallel? It's on an incline. And remember what I said, on an incline, my FG parallel is always going down the incline. So that means it will go in a different direction from the tension and the force of friction. So then tension, it will be tension plus F of static, and let's just also resolve the FG. So FG parallel, that is friction. So that means this will be what? MG. And because it's parallel, it's FG parallel. If it was FG perpendicular, it will be FG cos of theta. But now it's FG parallel. So FG parallel, that's MG sine of theta. Theta being the angle. So the angle that forms the incline. Okay, is equals to MA. Okay, now you come here, you ask yourself, now, okay, what happens? Because we don't have the value of tension, we're not giving the value of tension, but we know from the other block where we drew the free body diagram that tension is equals to mg. So tension is going up and mg is going down on the 2 kg block. So the same tension on the 2 kg block is the same tension on the 10 kg block. So then that will be 2 kg multiplied by 9,8, which is mg as well. So it's the same as mg. because tension is equals to mg when you look at the 2 kg block, and the same tension on the 2 kg block will be the same tension on the 10 kg block. So 2 multiplied by 9,8 plus, we are looking for the frictional force minus the mass. So but now obviously we are looking for, I used 2 here because I used it using the tension on the 2 kg block. But now this mg, we are looking at the 10 kg block. So that means if we're looking at the 10 kg block, here it will be what? 10 multiplied by 9,8 sine of 30 degrees is equals to ma. So that will be 10 multiplied by acceleration, but the block is not moving, the block is still, so that will be 0. So then ultimately on the right hand side we'll have 0. So then if we write friction as subject to the formula, we take 2 multiplied by 9,8 to the other side, so that will be negative 2 multiplied by 9,8 plus, because it's negative, plus 10 multiplied by 9,8 sine of 30 degrees. The other side is 0. 10 multiplied by 0 will just give me 0. Then my force of friction will be, if I add everything up, will be 29,4 newtons, and this will be up the slope. So that will be my force of friction. Okay, now we've calculated the frictional force. That will be the force of friction. Now we continue with the question. Now they tell us that the rope snaps above mass m. So mass m, that is just, they are just telling us that it snaps above the mass of 2 kg. So they tell us that the rope snaps. So when the rope snaps, that means the block of mass 2 kg, the block 2 kg will fall down, and meaning with the 2 kg not there to hold the 10 kg back, the 10 kg, that means it will also slide down the incline. That's just by observing. And the block, and they are told that block M falls to the ground. The kinetic frictional force between the block and the slope is 25 newtons. So that's for the 10 kg. Ignore the mass of rope T. So ignoring the mass of the tension. Okay. So draw a free body diagram of all the forces acting on mass M. So all the forces acting on mass M. So that's the 10 kg block. So if we draw a free body diagram, that will be normal force acting in this direction. Because now the rope is snapped, so it will be moving. So that means there will be force opposing it, which is the force of friction, kinetic friction. Then there will also be F of G downwards. Now you might think to ourselves, why didn't we put tension this time? I mean, last time we put tension, so I mean, surely there should be tension also. But remember, now the rope is snapped, so there's no longer really any tension pulling the block up. There's no longer tension pulling the block up. The block is now going to slide down. So there's no really, the only force opposing the motion of that object from going down, it's the force of friction. Tension is no longer there because the rope snapped. So that is why we're not considering it. Okay. Calculate the magnitude of the acceleration of mass m. Okay. Now we're calculating the acceleration of mass m. So this is when mass m goes down the incline, when it slides down. Okay. So F net is equals to ma. So remember, now when the block is sliding down, we only have two forces, force of friction and Fg parallel. That's the only two forces acting on that block because there's no longer tension. So we can say work, we can say FG parallel minus frictional force is equals to MA. Now this is mg sine theta is equal minus f of k is equals to ma. That means that will be the 10 kg multiplied by 9,8 sine of 30 degrees. And for the force of friction, we are given the magnitude of 25 is equals to 10, and we are looking for the acceleration. So that means we can put also on a calculator, divide by 10, and that should give us the acceleration. Putting that in the calculator, that gives me an acceleration of 2,4 meters per second squared. Okay. Now they're asking me to calculate the final velocity of block M. 2.5.1, final velocity of block M. Okay, final velocity of block M. So that means when block M falls down. So this one can be done two ways. I can use, from projectile I will have then the equations of motion. So I can use the equations of motion. Grade 12, if I'm in grade 12, I can use the equation of motion. Or I can also use the impulse formula. So I'll use both. So V final is equals to V initial plus A delta T. Now in this case, I'm looking for my V final. My V initial, I know originally that the block was standing, was at rest. It was at rest. Both blocks were at rest until the rope snapped. So that means my initial velocity was 0 plus acceleration. So acceleration will depend on my direction. But if I choose down as positive, that will be positive 9,8. And if I choose upwards as positive, that will be negative 9,8. But regardless, it will give you the same answer. So from this, we also told that this block takes 0,5 seconds to reach the ground. So V final is equals to 9,8 multiplied by 0,5, that is 4,9 meters per second. And this is down. And even if I had written it as negative 9,8, if I chose up as positive and wrote my acceleration as negative 9,8, I would have still written 4,9 meters per second upwards. Now another way, so I'll just write O here, or I could have said F net delta T is equals to change in momentum. So this would have been what? F net delta T, change in momentum. So F net, because that's the force of gravity, it's only the force of gravity, because remember the rope snapped. There was no initial velocity given to, it was not projected, there was no force applied to this block to go down. So that means the only force acting on this block as it's going down is force of gravity. So that means in terms of force, that's mg. So that's 2 multiplied by 9,8. And we're told that it takes 0,5 seconds to reach the ground, is equals to, remember, change in momentum, that's m v final minus v initial. So same thing here. So my mass, that's 2, and then my v final, that's what I'm looking for. My v initial is what? Is 0, because originally the block was at rest. So 2 multiplied by 9,8 multiplied by 0,5. Then this side I will have 2 velocity final. And then if I divide by 2, this 2 will cancel this 2. I will be left with 9,8 multiplied by 0,5, which means my v final will still be 4,9 meters per second downwards. Okay, so yeah, that's it. Now, that's the application question. How do you think would happen to the final velocity of the block M? So the same 2 kg block. What do you think would happen to it? The same 2 kg block. What do you think would happen to it if the mass was doubled and is dropped from the same height? So if it's still dropped from the same height, but the mass now is double, so the mass is now 4 kg. What do you think would happen to the um, velocity, to that final velocity? Do you think this velocity would change? Do you think it would increase, decrease, or remain the same? I mean, think about it. Some would think, oh, maybe it will decrease because now it's heavier, so maybe it will decrease, but that's not the case. In fact, it's the opposite. It will remain the same. And another way to check this is to just go back to your formula. If you get such a question, go back to your formula that you substituted and think about it. And let's just do that. Look, here we had 2, so let's just look at that. Because what we will notice is that because it's dropped from the same height, the height does not change. It's dropped from the same height. That means regardless of the mass, of the change in mass, the final velocity will remain the same. And think about it. If I had 4 here, I would divide by 4. I would divide by 4 both sides. This 4 would cancel this 4. This 4 will cancel this 4. I'll still have 9,8 multiplied by 0,5, which is V final. Even if I tripled my mass and got 6 kg, it will still be the same thing. They will still cancel each other until I get 4,9 meters per second. Reason being, my height is not changed. So because my height is not changed, it won't affect my final velocity because it's still being dropped from the same height. Even though the mass has changed, but it's still being dropped from the same height. And because it's dropped from the same height, it remains the same. Okay, that's all I had for today. Do another one on projectile and work energy. Thank you for watching, and don't forget to subscribe.